All right, so let's see. All right, so our goal for the next few lessons is going to be to work from something like this, a graph that shows the exact rate of change at every moment for something. In this case, it's for oil spilling. And the input is actually time. It doesn't have to be time as the input, so when I say moment, it sounds like it's always time. It doesn't have to be time, but what we want to know, if we have this exact rate of change function for every moment, how can we at least approximate what happens because of it? So, like for instance, if this was a graph of your speed driving down the road, you're driving fast and then slow and then sped up a little bit. But if I want to know how far you went, you need to do the regular sort of computations where you take a single number and MDX, your rate times a little bit of change in time. But you don't want to use too much time because your speed is changing all the time. Same with this oil spill, which is in reality what this is. So the oil's leaking pretty fast at the beginning, but it drops quickly also. So although I could say, oh, well, it's like 28 or so cubic meters per day, it doesn't do that for a whole day. So maybe I pick a shorter amount of time, like maybe half a day or some other random amount of time, and say, well, what if it did that? And then after half a day, I'll reassess what the speed is and use that for a little bit. And even half a day seems like a long amount of time. If we were computers, we could use like millions of different speeds that are shown here, because all of the, this line here isn't a curve that's like a wire bent around. It's a sequence of corresponding points. For every point in time between 0 and however far out we want to go, there's a corresponding speed at which the oil is leaking. So we could use as many of those as we wanted. There's infinitely many we could pick. A computer could pick 1,000,000 and do computations as estimates that would be really, really good estimates, probably indecipherable from in reality what happens, which will work out the algebra for how to do that, but that's much later in the course. But just as a starting point for now, what I want to do is do something that we can physically see. So we're going to use kind of unreasonably large chunks of time in which to do this. And what I'd like to do is use chunks of time that are, what I've picked here is 0.3 days. So imagine what this first line is representing that went across, that I use the speed that maybe is about 28 cubic meters per day for the first 0.3 of a day before I decide that, well, that's getting way too far from being accurate. But at least this way I can kind of see what's going on. I don't really want to draw little microscopic, but what I'm going to do is imagine that I'm using one rate for a little while, and constant rates appear as horizontal lines, like these two. So what this represents so far is, for the first 0.3 of a day, using this rate from time 0, which I could call it in precise form, I could call it r sub v of 0, but just for talking about it purposes, maybe it looks like about 28. So for the first 0.3 of a day, the oil's leaking at about, according to this blue bad approximation, but visible at least, approximation line, 28 cubic meters per day. And then I readjust, and at time 0.3, I'm going to say, oh, well, in the moment that t is 0.3, or by the time I'm at 0.3 days into this oil spill, the rate at which the oil's leaking is around 20 cubic meters per day. So let's use that for a little bit. And a little bit that's long enough for us to physically draw this would maybe, I'll just use this 0.3 again. We could use different lengths, but different lengths of time for the approximation, but it's a lot easier if you just pick one number and stick with it. That way you can have this kind of repetitive, every so often I'm going to change my rate estimate that I'll use. And so what I'd like us to do, and this is just arbitrarily chosen, is I'd like you to draw what I've drawn up here every 0.3 days up for the next, well, up to about there. I'm going to call this R without a subscript. So R sub V is that red curve, that's the exact rate of change function. I'm just going to call it in general R for a not fake rate of change function, but this is a piecewise constant graph. I've got 5 segments, each of which has a domain of 0.3 days. They're consecutive to one another, so with the 5 of them put together, what I've got is estimates for that I can use to estimates for the rate that I can use to measure how much oil is spilled. Now you can see the last one is really probably quite accurate because the graph between, what is that, 1.2 and 1.5 dips down and comes back up, and so the, just drawing it wise, the horizontal constant rate looks like it's right on top of that red exact rate of change, exact oil spillage rate. So this isn't what we're going to do all the time, but just for a second here, what I'd like you to do, and this is going to go away for a second, I know. We're going to do crazy looking stuff in a minute. But the value of the rate at this point is approximately maybe 28 cubic meters per day. During the second interval, it looks like, so just visualizing it, this isn't exact and this isn't really what we want to use, but just as a starting point to see what we can do with this, the second one has a value that's about 20. We read the rate value off of the vertical axis. So, meaning for the first 0.3 days, we're talking about oil spilling, oil being expelled at a rate of 28 cubic meters per day. Since we're measuring how much has spilled, not how much is left in the boat, that's why these are positive rates. But you can also see in the picture they're listed as positive rates, but it's drawn this way because we're not tracking how much is left in the tanker, we're tracking how much has spilled. So that's larger and larger, 28 cubic meters per day for the first 0.3 days, and then 20, and then if you look across the years, I don't know what this looks like, 1 mark up from 10, so maybe about, I'm just going to pick whole numbers, maybe about 12, it's probably 12.5 or something. I do actually have a function rule for R sub v, but we're just estimating anyway at this point, so let's just use this as an estimate. It's in a rough estimate. As you can see, the rates that we're using are almost always higher than, larger than, or faster than the actual rates because these blue lines are above the red curve, except for the points where they intersect, and maybe right at the tail end here. Let's see, where is this down to? That looks like about, what, 6 or so? So about 6 cubic meters per day, and then maybe 3. So again, this is just rough estimates. But looking at this, if I have this exact rate of change function that has infinitely many different values that apparently vary from around 28 down to something around 3 and then go back up, at least I've picked out at what some of those are. So if I wanted to know, for instance, just as a quick example, how much oil leaked during the first 0.6 days, using my estimate, not the actual function because that's got too many different values to deal with unless you're a computer, but using this estimate, I could say, oh, if I want to know what happened during the first 0.6 days, I know that oil was leaking at 28 cubic meters per day for the first 0.3 days. So the first rate times a dx, or times this 0.3, and then whatever happened during the second one, our second rate that we'd want to use, we also use for 0.3 days, a small amount of time. I can just talk about what happened during the first and what happened during the second interval, or we have 2 different speeds. Just like if you were driving for 40 miles an hour for half an hour and then 50 miles an hour for half an hour, you can add those 2 together to get how far you drove. Now, is that reasonable to drive a constant speed for half an hour at a time? Probably not, but we could still say you went, whatever that came out to be, 45 miles. So same thing here. If I have a rate and an amount of time, or input variable, whatever it happens to be, for which I use that rate, I can get that amount of change, the accumulation due to that first interval. So this is the oil spilled during the first 0.3 days and the oil spilled during the second 0.3 days. So we can talk about the sum of all of this as the accumulation so far. And so I could say, oh, well, this would be 28 times 0.3 and 20 times 0.3. So if I wanted to do a computation like that, I could. Now, what if I were to change this to something like the first 0.8 days? What would I need to add on to the end here using the estimates that we had here? If I want to know what happens, not the first 0.6 days, but the first 0.8. So here's, this is part of it, but there's a little extra. Yeah, so let's see, for the next, I need 2.2 extra days worth of oil spillage. And that would be happening at this third rate here, right? Between 0.6 and 0.8. All of that's like from here to there. So not all the way through that interval where we're using 12, but using this third rate of 12 for a little bit of a day. So we can figure out what happens during any amount of time. It doesn't have to be a integer multiple of this bizarre interval length that I picked, 0.3 days. It could be anything. We just have to figure out, well, which of these rates am I going to use? If I pick 1.4 days, it go through 1, 2, 3, 4 complete intervals plus 0.2 out of 0.3 on this last interval here in terms of using those different rate values. All right, so let me clear this off. So just this R here, and this is going to be our standard notation. It's used in the book. It's used in all of our worksheets, tests, whatever. When we're making this approximate rate function, you want to refer to using a constant rate for a while. We can refer to all of these horizontal pieces. This piecewise constant function has 5 different constant values in this picture as just plain old R. We're going to call all of them just plain R, no subscript. With the subscript, it indicates the exact one that we're working from. And without the subscript, it refers to this, oh, let's just use a few individual values, and we're going to use each of them for a little while. So picture-wise, you can say, oh, well, I'm just using the values at those 5 points. But if I wanted to graph a rate function that uses those, it would look like these horizontal lines, because I'm going to use each one for a little while as if that rate continued. So the idea is, though, that if I use these rates, I can model accumulation, and not just a total amount by a point in time, but I could graph what happens to the accumulation as I go along. So, meaning, meaning if for these first 0.3 days up to, there, and there's a picture of what we're doing. That one's not too scary. But if for these first 0.3 days, I start at 0 oil is spilled and change at a rate, this is a piecewise function, between time 0 and time 0.3, up to but not including. I just use the inequality notation here. You can, when you're writing it for yourself, you can use inequality notation or interval notation. GC doesn't like interval notation because it thinks you're trying to write coordinate pairs. But for the first 0.3 days, I'm going to use R sub V of 0. Now, when I was writing stuff earlier, I said this is about 28, but to be precise about it, that Y value is R sub V of 0. That coordinate point is 0, comma, R sub V of 0. It's on the red curve, it's also on the blue curve, or the blue, well, lines if you want. But if I wanted to model what happens during that first 0.3 days, I know it's increasing at a rate of R sub V of 0. To draw it, I'm going to use a number, about 28 cubic meters per day. And after one interval, just to be able to draw a picture of this, 28 cubic meters per day for 0.3 days would be, what, 6, 7, 8.4. So in the first 0.3 days, 0.1, 0.2, 0.3, 8.4, maybe about here. It's an estimate, so big dots cover error. In the first 0.3 days, it would get to this high. Now, if I want to draw a graph of what approximately what's happening, meaning a graph just using this constant rate function, not worrying about the fact that that's not actually what's happening because this second dot is based on using a constant rate. How would I get from this first dot to the second dot? Like picture-wise, straight line, curved line. If I'm moving at a constant rate of 28, yeah, straight line. Straight line with apparently a slope of 28. Now it's kind of hard to tell that because the scales of these axes are quite different. This is 0, 0.5, 1 versus 0, 10, 20. But pretend that's a straight line. Kind of hard to draw a straight line on this thing. But this would be a graph of what happened during that first 0.3 days. If this is a straight line. If I make it thick enough, it'll look like a straight line eventually. So if I wanted to write an equation for that line, or for that line segment, not just for the 8.4 where the endpoint is, but if I want to write an equation of this line, and for all the points on it, I know that it would actually be something with a slope of 28, or a rate of change of 28, starts from 0 and increases at a rate of 28. That's the rate that we're using. Or, to write it more precisely, it'd be r sub v of 0. But if I wanted to describe this line segment, I could say, I'm just going to write with y's and x's. Y equals 28x, because it starts at 0, right? And it goes up with a constant rate of 28. 0 plus 28 cubic meters per extra day past 0. So this is only because we're starting at 0 that it's pretty easy from here. Now, this only applies if x is between 0 and 0.3. And I'm going to say between 0 and 0.3 in that way, same as before. So including the 0, and at 0.3 we're going to actually change patterns. If I wanted to write what's happening in the next segment, I'm going to change colors for a minute. I know that between 0.3 and 0.6, I'm going to use this slightly lower rate. Picture-wise, it looks like about 20. The exact value of that is r sub v of 0.3, because that's this point on that curve has a coordinate point 0.3, comma r sub v of 0.3, which that r sub v of 0.3 is about 20 based on the picture. But if I wanted to write an equation for the line that goes from here with a slope of about 20, and over the next, to be able to draw this, we kind of want to know where it heads to. I'm going upward for an extra 0.3, or in other words, this is an extra 6 units that it's going to go upward. The endpoint isn't going to be down at 6. It's going to be 6 additional. Or if I wanted to know how much oil had spilled by time 0.6, just like what we did earlier, I'd say, oh, 8.4 plus 6, the amount that spilled during the first 0.3 days plus the amount that spilled during the second 0.3 days. So I'm starting at 8.4 and then increasing at this rate of 20, which makes me end up picture-wise at 14.4 by the time I'm at 0.6. So let's see if I can draw something reasonably accurate for 14.4. So if I want to write an equation of that second line segment, it's not y equals 20x. Would you agree? Because it doesn't start at 0, and if I were to extend this back, I don't really care where it starts. What I care about is this point. Starting from y initial plus m dx. I'm going to use this sort of thinking process here. If I start from this 8.4, and then go up at a rate of 20, I just have to be careful how I express dx, because when I wrote the first one, it was simple. That was because we were starting at the origin. We can think of that the same way, but this dx happens to be the same as x in the first interval, because in the first interval, how far I've used that rate is however far x is from 0. If I wanted to write this as y initial plus m dx for the first interval, I'd be writing 0, starting at 0, and add on 28, depending on however far x is from 0. Well, however far x is from 0 is just x. This all simplifies to y equals 28x. If I'm in the second interval, it doesn't. What I want to measure, this dx, the amount of time I've used this new rate, this rate 20, isn't the x value, it's however far x is past this circled point here, however far x is past 0.3. So I've got this 8.4 plus 20 times x minus 0.3. This looks like a weird equation for a line. This is point slope form in reality. If you've learned point slope form in algebra before, that's all this is. But all point slope form is describing separately where you start from, whether or not it's the y-intercept, and using both the x and y starting points, 0.3 for x and 8.4 for y. So start at the original y value and then change it at a rate of 20 for each incremental change in x past 0.3. I'm not worried about how far I was to the left of 0.3, that's where this 8.4 came from. So what we've got so far are equations for these two. This second one applies only between 0.3 and 0.6, but if you can see, we could continue this indefinitely. It's just a matter of, well, I'd have to figure out what this point is. Luckily, we know it's 14.4. So for the third interval, I'm going to change colors again. Let's see. For the third interval, I'm going to be using this rate, maybe about 12. So this is the numerical approximation. We're going to do this with symbols in just a minute. But if I want to use this rate, visually speaking, I'm like, oh, well, I'm going to go up by 12 for each additional day. Well, I'm only going to use it for 0.3 of a day. So by the time that interval is over, I will have gone up an additional 3.6, which I was at 14.4 by here. So if I go up an extra 3.6, that'll put me at 18. So we're accumulating. So by the time I'm at 0.9, I'm going to be up at 18. Now, we're doing all this numerically right now. We're not going to be using a whole bunch of numbers later, which actually makes this easier to write. I don't want you to spend your time doing computations, but if you don't know what it is that you're doing, it looks like a whole mess of symbols. So all we're doing is this sort of, oh, well, I want to increase at, again, a lower rate, which, I apologize, this doesn't look like a straight line. But for this third segment, again, if I think y initial plus m dx, my initial value for this third segment was 14.4, the ending value from the previous segment, plus my new rate, 12, times however far I am into that segment. However far x is past 0.6, because that's the length of time that I've been using the rate for if x is between 0.6 and 0.9. So notice that I didn't write down the number 18 here. 18 isn't a part of that equation. 18 is the endpoint of this. If I substituted into this equation x equals 0.9, I would get 18. Now, officially, 0.9 isn't supposed to be plugged into this equation, but for a continuous function, which this is going to be, those should match up. But the idea is each of these segments has its own rate, and it's really hard to sketch things that look like A, straight lines, but B, different slopes. But you can kind of see, if you remember the graph that I had before about what the exact accumulation looks like, it went kind of like this, up and over. Now this is a overestimate because all of these rates, other than at the very beginning, are too high. But we could continue this process indefinitely using each of these rates, and we could go farther and farther if we had more data, pictures to work from. I could continue doing this, this process. It is repetitive, which computers are very good at repetitive, but you need to be good at understanding how it's pieced together so you can express how do I explain what to do. And what we're going to work on over the next, so you're 2 weeks from today is when our test is. We're finishing this up between now and then. So this is not we're going to finish this by the end of today. This is we're working on this today, all of next week, and then maybe a little bit of wrap up on Tuesday before the test. But we're going to be adding in more symbols so that we can generalize this process, not to be about this specific curve where we used 20 and 12 and 28 and interval lengths of 0.3 days. We're going to do this for any interval length. And if you can write it for any interval length and any function, just express what needs to be done, then we can have as that interval length this 0.3 of just kind of using that as a parameter here. I could have made it 0.2. I could have made it 0.7. It's nice to keep one number throughout. But for the purposes of having a computer do some computations, you can make it 0.00001. And if you write it properly, it'll do the computations just as easily as if it was 0.3. Now, for you, doing with 0.00001 as your interval length would be horrifying. You certainly wouldn't want to try to draw a picture of it. But if you can express what needs to happen, which is really our keys here, our y initial plus mdx, if you want to write an equation for how much has accumulated due to the rate, so this is a net accumulation. Now, in this case, there's an oil spill. It started at time 0, so there was no oil spilled prior. If you remember the two bathtub graphs, one started at the origin and one started higher. All the difference between those is one extra number, and that would be, well, y initial for the first interval doesn't have to be 0. That's the only difference between those two situations. Nothing else changes throughout. But this is the premise that will allow us to write this. So let me show you this with more symbols, but to kind of generalize this and make it more precise. This 28, I mean, this is an estimate anyway, so it's not bad. But this 28 was just kind of approximated from the graph. The 8.4 was using that approximation. This 20 was approximated from the graph. And the 14.4 came from a whole bunch of approximations. We're like approximating on top of approximations. But if I just think about what accumulates during the first interval, we said it was 28 times x. Now, I was just using y's and x's because y's and x's are maybe easy to picture. But thinking about this was t was the independent variable, r sub v of t. So when t is between 0 and 0.3, the equation we wrote was 28x. And we said that's the same as 0 plus 28 times x minus 0. So I wrote the t minus 0 part here, just to be fancy. But I didn't write the 0 plus. R sub t refers to this function. If I'm between times 0 and times 0.3, writing r sub t means r sub v of 0. So I can write it that way if I want to, instead of writing the specific r sub v value. I can just say, oh, r sub t, because I've already defined, or r of t, because I've already defined r of t someplace else. If I want to talk about the second interval, remember we needed that endpoint from the first interval. So we need the result of having used this first rate, r sub v of 0, for the full interval of 0.3 units. So that means I'm going to have r sub v of 0 used for 0.3 plus whatever happens during the second interval, y initial plus mdx. So that r of 0 times 0.3, that's that, what was the number we had, 8.4, plus r of t here times t minus 0.3. Now I did want to point out one thing here. Notice I've got r of 0, well, actually two things I want to point out. I've got r of 0 and r of t written here. I could have also written r sub v of 0 and r of t, but I can't just write them all as r of t, because for any one t value, r of t has this just one result. It only has one value. So if t is between 0.3 and 0.6, like t is 0.4. If I wrote r of t here and r of t there, there'd be the same number. And I don't want the first interval stuff to have anything to do with the current rate. the rate in the interval, like the second interval in this case, the second chunk. So only the current interval is using this R of t notation, but I could write this different ways. I could write this as R sub v of 0, and this as R sub v of 0.3, and R sub v of 0. R sub v of 0 and R of 0 are the same thing. That's the fact that this blue dot's right on the red curve. So lots of times there's multiple different ways you can write this. I chose to write it this way so that the current interval, I'm always writing R of t, the exact same thing, because I defined R of t over here. You don't have to do that. We can just talk about function R sub v, the exact curve, and only ever mention those every so often sort of points, like R sub v of 0, of 0.3, 0.6, 0.9. I wouldn't want to say R sub v of t, because then that's talking about, well, as I go through an interval, it's going to keep changing. But if you can see, this gets more tedious, just like when we were doing it by hand. This is the equivalent of the 8.4 plus whatever it was. Something, the first two added up to 14.4, and then plus the third rate times however far we are past 0.6. So all of this blue stuff put together, since I don't have a numerical computation worked out, this is all the equivalent to the 14.4 that we had written before. This is equivalent to the 8.6, is that what it was? 8.4, and then 14.4 came later, and then there was an 18. But in any case, all of these, this is the accumulation from the full first interval, or using that highest rate for the first 0.3 days. This is using that next rate for the next 0.3 days. And then this is what's happening as I progress forward from time 0.6 to time 0.9. So at any point in there, after 0.8 days, the example that we did, we could figure out how much it accumulated. If I use this line of the formula, this is fixed, and this would be the 0.2 that we multiplied onto that third rate when we did the individual problem. So you can use this to evaluate at any point in time, but you can maybe see that this gets really tedious quite quickly. And I don't want you to focus on trying to write these ugly piecewise functions, because in reality what we're going to do is to try to write this a different way. Because you can see this is the equivalent of that 18 plus whatever happens during the fourth interval. However far we are into the fourth interval, multiply it by R of t for the fourth interval, which is R sub v of 0.9. And it gets even worse. So you can, there's a pattern. All this stuff in blue is that y initial, like that dot at the end of at the beginning of the line segment that we're just trying to draw. And then the R of t is the rate for the current interval. And the stuff in parentheses, t minus something, that's how far we are into that current potentially partial interval. So for any t value, any amount of time up to time 1.5, there's one of these rows of the piecewise function that would apply that would allow us to compute this. But I hope you would agree that this is pretty insane looking. I hope it's understandable in terms of like y initial plus mdx, or like point slope form for writing equations of lines if you stare at it long enough, but this is not an efficient way to write this or to do this. This is really messy, and if you wanted to do something where you changed rates every thousandth of a day, to get anywhere in this, if you're trying to write a function like that, it would take up multiple sheets of paper or tons of typing or whatever you were doing. Not pleasant. So, although I hope you can understand what each of these lines means in terms of a y initial plus mdx, I do want to show you how to write this in a different way. So let's kind of take a different approach. I want to use a different example, which in your book was a rocket basketball. Let's see. So start with a new function that we have a function rule for, as opposed to just here's a picture of R sub v. So we've got a team of engineering students designing a rocket-powered basketball for their course project. And they designed the motor so that within the first 90 seconds after launch, the rocket has a velocity of t to the 1.3 meters per second, where t is measuring the number of seconds since the motor started. So this is a velocity function. Now I've called it R sub h of t because this is a rate of change of, since it's talking about launching something, the rate of change of the height. So I just assigned the subscript h to this. We had v last time for the volume of oil spilled. So the rate of change of the height of this rocket basketball is given by that formula. And we've got a picture on the left where you can see that's what's actually labeled there as the velocity in meters per second. So it's a graph of the velocity on the left along with a picture of the ball rising on the right. And we don't actually know what height it was launched from. That doesn't impact what we're going to do. It looks like it's a little bit above the x-axis there, but it's a different graph. That's a graph of speed on the left, speed at which it's rising, and it's positive velocities indicating upward. And then we've got a picture of this ball going up. So if the velocity is doing that, I've got positive velocities, but it's not a constant positive velocity. It's a velocity that's getting faster and faster as time goes on. In other words, the ball's accelerating upward. So kind of rocket style, starts out slow and then moves upward faster and faster for the first 90 seconds at least. So thinking about writing symbolically, the sorts of things that we're going to need to write. See if you can answer these for yourself, discuss with your neighbors. I'll give you a minute or so, and I'm going to ask for responses to this. Stop this at 5. All right, so I paused the graph where t equals 5. So that blue dot at the end of the graph right now should have coordinates that are the ones asked for in the first question. How would you say exactly the coordinate point at the end there when t equals 5? 5 comma, yeah, r sub h of 5, right? I mean, I can look at this and say, it looks like about 8 point something. Now, we did actually see the rate rule on a previous page. It's not here. So if you happen to remember that, there's another way you can say it. R sub h of t was given by t to the 1.3 power. So I could say that the rate right now is r sub h of 5, but that would also be 5 to the 1.3 power in exact form. And if you wanted a decimal approximation, pop that into a calculator and see what it is, but looks like 8 point something. So r sub h of 5 represents the rate at which the height of the ball is, well, increasing in this case. It's height at which it's changing or varying. In the moment when t equals 5. So I don't want to say it's at like something like instantaneous because, well, if you haven't moved anywhere, you aren't changing. So like in this picture right now, nothing's happening. But if I allow t to vary just a little bit away from 5, I'll see a change in the height of the basketball, and that height would change at a rate given by, well, mdx, r sub h of 5 times that little amount of time that I allowed to pass. So it's the rate of change of the rocket's height at the moment t equals 5 seconds. And again, moment, remember, means a small increment of time, or you can think of it as a small variation in time, or allowing, you have to allow some time to pass for rate to accomplish anything. So it can be really, really, really small, but it can't be no time. So again, just interpreting this, the height of the rocket in meters will, I can see it's increased because it's a positive number regardless of anything else that we might want to estimate. It's definitely a positive value. The height of the rocket in meters will increase by r sub h of 5 times that small amount of elapsed time, or that small increment of time that we allow to pass. But it has to be an amount of time around t equals 5. So if I wanted to write that in symbols, this is a dy equals mdx, or in this moment, the height is varying by r sub h of 5 times a small amount of elapsed time. Now, I'd have to actually be playing this for anything to be varying, but during any moment, not just around t equals 5, during any moment that I have a rate associated with, I can use that rate and do the same thing. Find an incremental change in height by multiplying the rate in that moment times a small amount of time passing. Just measure the time in seconds, and we'll get the increase in height measured in meters. This velocity is in, I don't know if you can see this, meters per second. It doesn't say meters per second anywhere else on this page. It was on the first page. So if I wanted to start estimating accumulation in height, like I said, I don't really know if this was starting at 0, but due to this rate, we can just talk about how much extra height we've accumulated due to the rate, and if we happen to get information about the height the rocket basketball was launched from later, we can just add that on as one extra number. That's not going to change what we do with our rate. But on this one, instead of 0.3 days, let me just use 0.9 seconds. Just arbitrary choice, because if I use 1, it's going to be really boring looking and gets confusing. So I'm going to, the 0.9 makes it look a little bit more awkward, but we can see what we're doing as opposed to just thinking we're writing a rate. It's a rate times something, which times 1 just makes half of our work look like it disappeared. So to start estimating the height accumulation due to this velocity, let's do what we did last time. Start highlighting points every 0.9 seconds, starting at the launch. And so to talk about this sort of setup in general, because this is the same process we're going to use. We're just not going to write a piecewise function this time. I want to give us a symbol to call this. I'll call this delta t for an increment of time. Now, I don't want to call it dt. There's going to be a dt and a delta t that we're using. dt is a variable that I allow to change from 0 to however far, but small. It varies within a small interval. The interval width that I'm going to allow it to vary in is this 0.9. So delta t is like our domain size for dt. dt is a variable that changes from 0 up to, and I can talk about all the different amounts of change in the height as dt grows from 0 to at maximum 0.9 in this case. But delta t is just that cutoff point. This is the maximum size of my domain that I'm going to allow for my differential, for my dt. So this delta t equals 0.9, this kind of, let me just pick a number like we did last time. This is a parameter, so it's not going to change sizes. I'm going to use the same number in a bunch of different places on the x-axis in terms of separating or measuring 0.9 units in a bunch of locations, but it's just one number. So this makes it a parameter. I've got a symbol for it, and it's a symbol that has a single value. I could change it for a different problem, like the last problem, the equivalent was 0.3 days. I didn't call it anything, but if I assigned a value to that 0.3 days, that value or that symbol would have been a parameter. So what I'd like you to do, just thinking about this, is sketch an approximate rate of change function using the rate at the left side of each interval to define the constant rate for that interval. So, well, it says that, but rather than having like extra pieces of paper, trying to save a little paper, what I'm going to pass out to you is one that has it already done. But let me just pause and do this. So thinking what we did last time, the first interval, I'm going to use the rate at the left side of this for the next 0.9 seconds. And then after 0.9 seconds, I'm going to pick a new rate and use that for 0.9 seconds. And so on, using constant rates. These horizontal lines aren't just for fun. The horizontal lines are to indicate that, well, horizontal rate graphs indicate constant rates. So let's see, 1, 2, 3, 4, 5, 6, 7. This is also posted on Canvas. It's posted on Canvas also if you want an extra copy of it that isn't drawn on. Because we're going to be writing on this and drawing on this. And there's two sides to this one. Task 1 and task 2. So this one has the rate function already drawn on it. And what we're going to do is similar to what we did last time, only we're not going to write a piecewise function. We're going to start from just writing a sum that indicates a single line of that piecewise function. Alright, so the side that says task 1, on the picture, there's pictures on both sides. One side says task 1. Alright, so I'm going to pull up my slide that says the same thing. So just to see kind of where that graph came from, here's the computer drawing version of what we're doing. Yeah. Oh, sorry. Sorry. So this is all the way generated from left to right using delta t, an interval width of time, kind of subdividing this into intervals of width 0.9 units. And during each of those intervals, we're using a single rate. Now in this graph, both the one you have in front of you and the one that's up here, it doesn't look like there's anything going on between 0 and 0.9. Why is that? Like, I can't see the graph. Did we skip it? Yeah, it's 0. So the rate for the basketball at time 0, that t to the 1.3 power at time 0, or at the moment t equals 0, would give a value of 0, 0 to any power 0. Well, at least 0 to the 1.3 is 0. So if I use that rate at time 0 for the first 0.9 seconds, that means I'm using a rate of 0 for a while. So it's just right along the x-axis there. So there is actually a first segment of this horizontal piecewise constant approximate rate function. It's just that it's right on top of the x-axis, so hard to see. And if we did what we did last time, doing some numerical computations and using a different constant rate for each interval, we'd get a graph that looks like this. Only when a computer does it, it's a little neater. So here's what you have. Suppose that we want to figure out, so this is like at the beginning of what we're doing with oil spill and everything. Well, how much oil was spilled during the first 0.8 days or something like that. I want to do a numerical computation here. You can use numerical estimates, but we also have function notation we can use, or this function rule. You can write that. So don't bother grabbing a calculator to try to compute things, but what I'd like you to try to do is figure out how much the rocket had risen between time 0 and time 5. So this isn't necessarily its overall height, because we don't know what height it was launched from, but how far it rose between time 0 and time 5 using this approximate rate graph. The approximate rate graph gives us rates. We're going to use the first rate, which is 0, between time 0 and 0.9. And then this next rate, if I wanted to refer to this second step here in this piecewise step function, I could call it, let's see, since it starts at t equals 0.9, I know its height is r sub h of 0.9, or I could also call it 0.9 to the 1.3 power. So where it says symbolic and numeric, try it once with function notation, try it once with things like 0.9 to the 1.3 power. Sort of numeric, but don't bother working them out expressions. So this is like working out a part of a single line or evaluating a single line of that piecewise function without writing out the piecewise function. How far did the rocket rise between time 0 and time 5, which is where this graph is frozen right now? So you don't have to have a number answer. It's going to be like symbol and numerical expression sort of answer, but take a few minutes. See if you can write out what needs to happen to figure out how much was accomplished using several different rates, not infinitely many, but just several different rates between time 0 and time 5. So think about where each of those intervals starts and stops, each of those delta t intervals, and what these two lines are about. It's kind of split up into two parts. You might notice that delta t equals 0.9 isn't going to mean that 5 seconds isn't 5 full intervals or 7 full intervals. It's going to be a weird number of intervals, like 4 and apart. So t, you can see in this, is in the middle of, or t equals 5, is in the middle of this interval here. So there's 1, 2, 3, 4, 5 full intervals of width 0.9 for which we're going to use different rates, and then a 6th interval that we're going to use part of. But if you figure out where each of these intervals starts and stops, you can figure out where we're going to evaluate our rate function and how to measure the accumulation over 5 seconds. And by accumulation, I mean the height that was gained during those 5 seconds. So there's one part of this task description that I didn't read this part, this left side approach. I just wanted to point out the way that we decided to estimate the rate function is one specific way. Like, we're setting up our interval width of 0.9 seconds, and then we're going to, starting at time 0, we're going to use the rate from time 0 for the next 0.9 seconds. Or in other words, that interval that lasts from 0 to 0.9, we're using the actual or exact rate from the left end of that interval. The rate at 0 applies to the next 0.9 seconds. And then the rate at 0.9 applies to the next 0.9 seconds. Or between 0.9 and 1.8, the rate that we're using is the rate, the actual rate or the exact rate from the left end of that interval. So that's what's meant by this left side approach. And there's multiple different approaches, but in the end, when we make delta t extremely small, which is going to be our goal, they all turn out to be the same thing. So there's no need to do it a bunch of different ways. We're just going to stick with one way and then get to our methods of making this easier. So you'll see left is mentioned a few times throughout this. It just refers to that, oh, that's the left end of the interval is where we're getting our exact rate from. Or we're getting our approximate rate from the exact rate at the left end. So during these complete t intervals, so these intervals start at 0, 0.9, 1.8, 2.7, 3.6. This one would be at 4.5. We only do part of it before we get to 5. So for the complete t intervals, we're using the exact rate values at those t values I just mentioned, 0, 0.9, 1.8, 2.7, 3.6. The exact rates at those 5 spots, the first one happens to be equal to 0, so you could write that another way, but each one times the length for which we use it. So to compute this approximate net change in height by one point in time, this is a numerical computation, but we could write it with function notation and symbols to express what we want. The exact rate at 0, 0.9, 1.8, 2.7, 3.6. Each one times, well, 0.9, which is delta t. Or we could write with using the t to the 1.3 power function rule. And using the number 0.9 or some combination of those. If you had r sub h of 0.9 times 0.9 and r sub h of 1.8 times 0.9, that's fine also. But realize that these two rows say the same thing. They're each telling us to add together 5 full intervals worth of accumulation in height, although the first interval, that's going to be 0. Maybe an easy numerical computation to do. So if you just wrote that as 0 or didn't write it, that'd also be okay. But realize that that is 5 full intervals or 5 complete intervals, plus we've got one last interval where I don't want, if I was writing symbolically, I wouldn't want to put delta t here. I'd call it something else, dt, however far t is past the beginning of the interval. So you could also write instead of dt here, like we did on the previous example, you could do t minus 4.5, which is the value of dt, how far we are past the beginning of the interval, which happens to be 0.5. There's an extra 0.5 since this starts at 4.5 and we're stopping at time 5, t equals 5. So adding all of these 1, 2, 3, 4, 5 complete intervals accumulations plus one of a slightly different size, a 6th intervals accumulation. I just have these separated because these all have something in common. They're set up very similarly. It's a rate times 0.9 or a rate times delta t. This one doesn't have that 0.9 or delta t in it. It has a smaller value. So I just put it on a separate line. But you may or may not have worked a lot on this in previous classes. If you have to add up a whole bunch of terms that are fairly similar, there's only one thing that's really changing from one of these terms to the next in numerical form, like what number is raised to the 1.3 power. Or in the symbolic form, it's where am I evaluating r sub h? But everything else is the same about each of those 5 terms. What we're going to be building toward is writing this as a sum, using a big capital sigma notation, and saying, oh, it's just a sum of a whole bunch of things that are like this, plus there's going to be one stray term that doesn't quite fit in the summation, so we'll have to write it separately. There could also be a plus initial height that the ball started at sort of term that we wouldn't get from using the rate at all. That would just be something, whole separate question, how to figure out height as opposed to just accumulations in height or gains in height. But our premise that we're working towards is, since a lot of this is the same for any value of t, this was a specific question, find the approximate change in the height by t equals 5 seconds. But if I can change from trying to write this as a, and I copied this just for your own, like, maybe horror, we could write this out again as a piecewise function. But in reality, to answer any question, I can just think of, well, I'd like to, for any question, t equals 5 seconds, I can even just call it t equals any number t seconds, and then put t somehow in this and tell me, well, I need to add up a bunch of pieces, each of which is like this, and is the same width y. Plus, potentially there could be, depending on what value of t I have, there could be some extra term. If I can write a kind of one-line formula that does all of that, then we can skip this stuff, which is, as you remember, unpleasant. I can write the rate function part is easy enough. It's just, oh, use the r sub h of 0 for the first interval, r sub h of 0.9 and the second, and so forth. And for writing the accumulation, just net accumulation in height. And I call this A of t, A for accumulation, to remind us we're not actually calculating the height of the basketball. We're just measuring the net change in the height from time 0 towards whatever, or just changes in height due to the rate. It doesn't take into account any like initial height. That would just be one extra term though, initial height plus whatever happens, A of t, where this is just going to be the same as what we did on the rocket basketball one, or the oil spill one. Well, I initially start with no height's been gained, and then I use either, I can call it r of t, referring to that whole thing, or I can call it r sub h of 0 during this first interval. And then during the next interval, I have a starting value, y initial, plus m dx, however far I am past 0.9. Again, just thinking of the current interval, wherever we are in the middle of something else. And we could go on third interval, fourth interval, and it gets ugly, so I'll stop. But this is the same setup as last time, and all of these can be done the same way, regardless of whether I have positive or negative rates, regardless of if I pick 0.3 or 0.9 or 0.001 for that delta t. But instead of worrying about all of this, if we can think of the general process of, what do I need to do? I need to figure out how many intervals I've gone through to get this approximation, and what delta t I'm picking to figure that out. That's a key part of it. If you're using extremely small delta t's, computers don't care if you've got 50,000 lines of this. Like, okay, I'm just going to add together a bunch of stuff. Doing this manually, we hope it's only a few, like that, like after 5 seconds. We can add together like 4 or 5 computations, but it gets really repetitive. And repetitiveness is good for computers. It's good for summation notation. It's good for a lot of formal notation usage in math. It's not good for computation, but we'll let the computers take care of that, computers and calculators. So there has to be a way to use math notation, as I said, to write these types of piecewise functions more quickly. So what do we need to be able to put this together? And this is, again, what we're going to be working on slowly between now and your test. To find the approximate rate function's value at time t, we need the left end velocity for any interval. So I need to come up with somehow, say, all right, so if I'm given a value of t, by which I want to know how much has accumulated, I need to know the rate at the left end of that interval, and, well, I also need to know the rate at the left end of every interval and add together a bunch of stuff. But to find just the rate function's value for any time, all I need is r of t. Thinking about that rate at the left end of the interval. So, okay, I need a way to describe, find the rate at the left end of the interval I'm in. We'll work on that. Not easy. We'll come up with some notation to describe it succinctly, but it does involve, in the background, some other math functions. If I want to find the approximate net accumulation up to time t, from time 0 through time t, well, I need to know kind of like how many intervals I have, the rate that I use for each one, and if I'm in the middle of an interval, how much of that interval I've used that rate for, like that, all the complete intervals plus whatever partial interval or current interval t is in the middle of. So for each of the individual intervals, it's just m dx, m dx, m dx, or m delta t, m delta t, m delta t, till I get to the last one where I have to think, well, what's the amount of time or the amount of independent variable variation that's happened into this last interval, the one where I'm currently placing my value of t. But I have to use all of the stuff that happened previously. I can't just pick an individual spot, so it's not a simple process. However, summation notation helps us with this. So quick algebra review for today before we leave, and I'm going to give you some things to think about for over the weekend to prepare for kind of combining summation notation with what we were talking about in these rates and accumulations. So if you haven't seen this before, this will be a brief review. Realize that you're going to be doing a lot more with summation and rewriting and analyzing them in calculus too. But for our purposes, what we need to understand is what the different symbols in the different places mean for us to do. So this expression right here, there's a lot of different orders in which you can read all of the parts, but this would typically be read maybe as the sum of the expression 5n plus 6, where n takes on all the values from 0 to 4. Now, it's not taking on infinitely many values, it's taking on integer values. So 0, 1, 2, 3, and 4. So I'm going to use 5 different values of n, 0 through 4, sub them each into that expression, and then add them together. So I'm going to put up 3 questions here. The first one I kind of explained how it works. So if you haven't seen summation notation before, this could be a little bit weird looking. If you have, the first one you can probably see is pretty easy. What I mean by question 2 is fill in those 2 blanks where the parentheses are so that it comes out to be exactly the same sum and result as question number 1. So that n that's down below, or the j, or the k, those are called the index of the summation. It's kind of like a variable, it's just kind of, we're just using a symbol as a placeholder that takes on a bunch of different integer values. And most of the time they're even just whole number values, although we can use negatives. So I said that first one there, just what it means is to substitute in the numbers, whole numbers, 0 through 4, into that expression 5n plus 6. Sometimes you'll see parentheses around it, especially if there's a lot of other stuff around, but if it's hanging out on its own, you'll not always see parentheses around the expression you're subbing into, the summand. But subbing in 0 through 4, we should get those 5 results, which if you do the addition, it comes out to be 80. So think about something you could write in each of those sets of parentheses in number 2 that would make this come out exactly the same as above. Notice it starts at the bottom with j equals 1. So I'm going to use an index j and let it vary from 1 to something, and then sub it into some slightly different expression probably, so that it works out to still mean 6 plus 11 plus 16 plus 21 plus 26. And the last one just uses function notation, where we've got a k, but a function that's defined at the left. All right, so any thoughts on number 2? What could I put, what would I need to put at the top of the sum so that it adds up the same number of pieces? Yeah, 5. So 0 through 4 and 1 through 5 is the same number of things to substitute in. So again, the number at the top isn't how many, it's the last number. So the number at the bottom is the first number you substitute in. The number at the top is the last number you substitute in. And to figure out how many it is, I subtract and add 1. But 1 through something is easy. So this would be 1 through 5 on top of the summation. If I want to substitute in the numbers 1 through 5 into this expression and have it come out to be 6, and then 11, then 16, and so forth, what do I need inside the parentheses? J minus 1. Because if I put J minus 1 here, and J starts at 1, the first time I sub in, it turns it into a 0. Cool? Which would be exactly like subbing in n equals 0. So the letter of choice doesn't really matter. J or N or K. But you can write sums a variety of different ways, have them be equivalent. If I do 1 through 5 and then put in J minus 1 here, this would come out exactly the same as that, the same 5 things added together. And so the sum is still 80. So in question 3, this is adding together the results of substituting in k equals 1 through 3 into this spot. Just realize that this is multiplication of 3 times a function value. So 3 times f of 3 plus 3 times f of 5 plus 3 times f of 7, which would be 3 times 3 squared, 3 times 5 squared, 3 times 7 squared, which is 249, but that's not the important part here. So we will be doing some summation work, trying to figure out how to write our accumulation more succinctly using this form. And it takes a bit of work, and there's going to be a lot of symbols involved, but if you understand what the pieces are, it's the same pieces as what we used before. All right, I'll see you next time. Have a good weekend.
I've been having some problems with graphing calculators.
Okay.